Okay, so in this chapter, we're talking about chapter 2a, and chapter 2a talks about motion in one dimension. So we'll be talking about the different physics formulas which govern how all things move. So over time, people did a lot of different investigation, and they came up with some thoughts, and they did some experiments, and we now have laws which talk about how objects move under constant velocity or constant acceleration. So in this chapter, what we want to do is learn about the symbols in those formulas, and see some sample problems dealing with those formulas. So we're basically talking about motion in one dimension, so either horizontally or vertically. So the way I like to teach physics is to use something called the Cartesian coordinate system. And there's a lot of different ways you can talk about an object moving, but I'd like to be consistent and try to use this same system throughout the whole course, and that way everybody's kind of on the same page. So the way I do it is based on the number line. So in a math class at some point in life, you learned about the number line, where this was 0. And if you went to the right of it, you would say it's positive x. And if you went to the left of it, you would say it's negative x. And then you learn about this piece. And if you went in the upward direction, you would talk about the positive y, and the downward direction, the negative y. So using this, this has a name, and we call it the Cartesian coordinate system. So using the Cartesian coordinate system, and every math class use something like this. When we start at the beginning, that's the origin, that's at a position x is 0 and y is 0, and then as we move, if we're moving to the positive x direction, we'll go this way. If we're moving to the negative x direction, we'll go this way, to the left. And a lot of times, if it's a top view and they're talking about people traveling, they'll use the idea of a map, and with a map, you could superimpose, if this was a top view of a neighborhood, we could superimpose the words So if we had a map there, we could superimpose the words north, south, east, and west. So if you had an object traveling to the east and you want to draw it, you could just draw it this way and have something traveling in the positive x direction. If they stop and then turn and travel to the north, well, from this point, then you could have them traveling in the positive y direction. Okay, so we use it. It's officially called the Cartesian coordinate system. It's named after a person named René Descartes, who was a famous scientist, a famous philosopher, a famous mathematician from France. And Carte is right there, and his name is René Descartes. So, kind of, it's named after him. Okay. So if we had a person who was just standing somewhere, we could use the x-axis. Talked about the negative x is going to the left and the positive x is going to the right, and here could be 0. So we could have a person standing right here at just a certain position, and this could be their initial position. So your initial position, right here, let's just give them a number. So this person could be standing at x equals 7 meters. I just made up a number of 7. Okay. Now, usually we want to distinguish the beginning pieces of information from the later pieces of information. So what they do is they usually give this a little subscript 0. So the subscript 0, it's pronounced x naught. And naught in this case would be a counting number. It would basically be, 0. So x at the beginning would be x subscript 0. And they don't say 0 there, they just say naught. It's an old-fashioned way of saying 0, actually. Okay, so and then the person could move. Now, if they moved, it doesn't matter where they moved. They could move to the right or they could move to the left. If we had the person moving to the left, the person later could be walking along this way, and they could stop anywhere at all. We could have them stopping at right here, taking a tiny walk, and this could be their final position. And we could call this point here x final, and we could say that is -4 meters. And that F is for final. Okay? So you'll get questions, and you'll have to talk about how the object is moving. Okay? There's two ways to talk about the object and how it's moving. There's one way, and we call it distance. And when you see the word distance, distance really means the length of travel. Distance is something called a scalar. They talk about that in chapter 3 of this textbook. A scalar is a number which doesn't have any direction at all. So when they're talking about here the distance of the person, we don't know what just happened. We don't know if they've just walked to the left or to the right or to the north or to the south or to the east or to the west. We don't really know. So by saying distance, it gives us some information, but it doesn't give us a whole lot of information. For instance, if you were to tell somebody that you work, if you were at work and someone said, "Where do you live?" If you say, "I live 20 miles from here," it doesn't tell them a whole lot in terms of which direction do you live. If you work in Boston and you tell someone you live 20 miles, they don't know if you're a North Shore person or a South Shore person. But if you said I live 20 miles away from work to the south, it gives them a little bit more of information. So when you give a direction, it's a little bit more informative. It's a little bit more technical. And what we call that the displacement. So instead of talking about a distance, we want to talk about something more technical called a displacement. And the displacement is basically it's the straight line distance from the starting point to the ending point. So the displacement is a straight line distance from the starting point to the ending point. Okay, we have something in physics that we use an awful lot, in science classes actually, and it's called delta. So this little triangular shape right here, it's a Greek letter, and it's called delta. So we would say here, this is delta x. So I've written it here. When you see that triangular shape, you could have any letter near it. We could have delta time, we could have delta temperature, we could have delta anything. Delta x is the change. How is something changing with respect to time? So later on, you see, the person here is going to be moving. So they're going to be moving their position. They have an initial position, and later they're going to have a final position. So delta x is written this way, delta x, and it equals the change in x. So what does that mean? It's also written as the final position in this case minus the initial. So whenever you have delta, it's always going to be the same thing. It's going to be the final first thing minus the initial thing. So in this case, we're talking about delta x. X is a symbol that we use for the word position. So the final position minus the initial position. If it was temperature, we would say the delta T, temperature, would be the final temperature minus the initial temperature. If it was delta time, we would say delta time final equals delta time initial. So So we always put the final piece minus the initial piece. That's important. So in this particular case, we would come up with the final position is -4. And then we'll say minus, the initial position was a +7. And when we plug that in, it comes out to be -11 meters. In physics, we don't really want to talk about distance too much. We usually want to talk about something called displacement. Displacement is how the object has been displaced from the starting point to the ending. So this right here would be my starting position, and this would be my ending. And if we want to know how the person was displaced, we would say delta x, which would be the final position minus the initial, and in this particular case, it is -11. They have been displaced. They have been moved 11 meters. Negative means to the left. So they've been displaced 11 meters to the left where they've started from. Okay. So this delta x piece is also called the displacement. So if they're talking about delta x, when you see the letter delta x, it's going to represent displacement. Some object has been moved from its initial position to its final, and the sign in front of it means it's a vector, so we will know about the direction in this particular case. So here's a quick example to show you what is the difference between a distance and a displacement. So here's what happens. Somebody is just on a straight street. It's pointing between the north, the straight street is pointing between the east and the west. So if I draw the street here, and the person is going to just go for a walk. So if we just call this here 0, this is too big for units to be going for a walk. So the person's going to be going for a drive. So this is in kilometers. So let's say that the person were to drive 50 kilometers going to the east. So what they would do is they would go over here and they would be driving 50 kilometers. And then they'd end up at this point right here. Okay. So this would be the start, and this would be the end of the first part of their trip. And then it says, then they're going to have to turn around for some reason, and they're going to have to go west 20 kilometers. I don't know why they're going west, but they have to go west now. So, you see, for the second part of their trip, they're going to go to the west. So they're going to start right here and go this way. And that arrow would represent 20 kilometers. And they've gone to the west. The arrowhead here is showing me, if you consider going to the right, positive x, or east, then going to the left would be negative x, or west. See, so that's what I'm doing here. So now, this is the second part of the journey. This is the part right here. They've started at this location, and they're now traveling 20 kilometers to the west, and they're going to end right here. Then what does it say they do? Then they have to turn and drive 40 kilometers to the east once again. And again, I don't know where they're going. This seems like a crazy type of a trip, but they're going to start right here, and they're going to go this way 40 kilometers. So this line in red here would be 40 kilometers. And they're going to end right here. Okay. So this is the overall ending point. And this position here was the overall starting point. So if you were asked just simply, what is their distance that they traveled? The physical distance that they traveled is those numbers going, that their car's odometer would be just collecting the data as they drive along. They physically drove through 50 kilometers and then 20 more kilometers. That would be 70. And then they went 40 more kilometers, and that would be 110. So if you add up all of these kilometers, the car physically traveled through 50, and then they went backwards 20, and then they went forwards again 40. Their odometer would have gone through 110 kilometers. But so distance equals 110 kilometers. But displacement is something else. Displacement is called a vector. Okay. So displacement is given a symbol, delta x. Distance is not given a symbol. So delta x, what does it mean? It means find this ending point right here and subtract away this starting point. Okay. So what position are we at? Well, in this particular case, we were at 0, and then we went to 50. Now, right here, when we were here, we went from 50, and we went back to the left 20 more. So if you had this as being a point 50 kilometers on the chart, then back here, this particular point on the chart would be 30 kilometers right here. And if you take 30 kilometers and you add in red the 40 more, 30 plus 40 would give you 70. And that's your final position. So delta x would be the final position, 70, minus the initial position, 0. If you wanted to get delta x, it would be 70 kilometers minus 0 kilometers. So delta x would be a positive 70 kilometers. The positive piece there means we're going to the east. So that's the difference. It's just one car. The one car is traveling, but the one car traveled through 110 kilometers, but the one car is only displaced by 70 kilometers to the east. Okay, let's do another quick example with this to show you how sometimes it could be tricky. So let's say that there was a racetrack, and it was a perfectly circular racetrack, and let's say the circumference, the distance around the whole racetrack is just a nice even 100 meters. So this has a distance around the whole racetrack of 100 meters. Okay, so let's say you want to get in shape, and one day you go out to this racetrack, and you start right here, and you end at the same spot. So you're going to start right there, and you're going to walk around once, and you're going to end right at the same spot. What's the distance that you traveled? Well, the distance is just the physical length of travel that you go through. So if you had a way to measure with some type of a pedometer or some type of a GPS personal system that'll tell you what you've walked through, it should tell you that you physically walked through a distance of 100 meters, because that's how long the track was. But what happens if it says, what is your displacement? And displacement, remember, is called delta x. I'm sorry, I'll write the word displacement. So in this case, the delta x is called the displacement, and in this case it equals 0 meters. How did I come up with 0 meters? Well, we started on this little dot here, we walked around the entire track, and we ended on this little dot once again. So we have been displaced by nothing. If we end on our starting point, then we're not displaced. To be displaced, you have to talk about moving from point to point. Okay, I'm standing right now to the left of the screen on a certain spot. If I step over here, then I'm standing to the right of your screen, and I have just been displaced by just a few feet or a meter, maybe. If I start here and I end here, and I try to draw a straight line from the starting point to the ending point, my line would be a length of 0 long. So this would be a tricky question. Even though the person ran through 100 meters, they have not been displaced by 100 meters. They've been displaced by 0 meters. So I would recommend drawing out all these problems to see the situation. Okay? If it's a straight line motion, the displacement and the distance would be the same. If you just decide to drive east for 5 miles, straight road, whatever, 5 miles exactly, well, your displacement and your distance would be that number, same number, 5 miles. Okay. your average speed is defined as the distance that you travel through divided by the time that is passing as you travel. So when I write average speed, it's defined as average speed. It's the distance your car is going to move through, the distance the object is going to move through, divided by the average, divided by the time that has passed, the time that's elapsed. Okay. The standard units could be meters per second. Standard units are meters per second, but you can really use any units whatsoever, as long as we're not talking about an object that's accelerating. So if we had an object that was traveling at an average speed, for instance, if you took a trip up to New Hampshire from Boston, you might find that in the Boston area, your average speed on the highway might be something like 10 miles per hour, and it might take you about an hour to get out of the Boston area, and then you might find that your average speed well north of Boston might be something like 60 miles per hour. So we didn't accelerate there. We were stuck in a very trafficy portion of the trip during the first hour of our trip, and then the second part of our trip, we were in no traffic. So as long as we're not accelerating, we can use any type of unit. So units like kilometers per hour are okay units. But the standard unit should be meters with seconds, and we learned about that in Chapter 1, what the standard units in physics would be. Okay. Now, if we want to talk about the average velocity, so we just talked about the average speed. If we want to talk about the average velocity, we would write it as a formula, and the formula is written this way: delta. Delta, remember, means the triangle is pronounced delta. It means the change of. It means the final piece minus the initial piece. So we would talk about delta x, which we say is the word, the displacement, divided by delta t, which we say is the word, the total time that's passed, or the elapsed time involved. So we could write it as a formula this way. This is in your book. They say the average velocity, and they put this little arrowhead on top of it. The little arrowhead is telling us this is a vector. A vector just means it has directions associated with it. So the only thing that arrowhead is trying to tell you in the book is it's a vector quantity. So it means the final position minus the initial position over the final time minus the initial time. Okay? It's not the exact same thing as the average speed. The average speed is something called a scalar. You'll learn about scalars in Chapter 3. The average velocity is called a vector. I should have written that bigger. It's called a vector. And a vector is simplified with that arrow on top there. A vector is just a number that has a direction associated with it also. So these are definitions. You've used this definition quite a bit in life, I'm sure. If you've gone to take a journey anywhere, you might just, nowadays the GPSs will tell you exactly when you're going to get there, so you might not have to think about it. But not too many years ago, if people were going to go up to ski country, they might say ski country is about 200 miles away where they're going, and they might say it's 200 miles, so I have to travel a distance of 200 miles. And then they might say, my average time can probably be about 50 miles per hour. So in your head, in their head, you might say 200 miles divided by about 50 miles per hour, and you can expect to be in the car for about 4 hours of wait a minute. You might do this. You might say the distance traveled is going to be about 200 miles. And you might say, on average, I can do approximately an average speed of something like 50 miles per hour. So if you just look at this math equation, if if this is 200 and this is 50, in your head you would figure out that you'd have to be in the car for approximately 4 hours to do that. So this is a formula that people have used quite a bit. In most math classes, the first algebra formula that you see when you're doing word problems, the first formula they often give you would be something with a car traveling down the road. And they'll talk about the average speed and the distance and the time, and it relates here. Average velocity, remember, displacement is a vector, so the displacement is not always the exact same as the distance. Sometimes it is. Okay, so here's a trick question for you. Let's go back to that racetrack we had a little while ago. So here's a racetrack. The total distance around the racetrack equals 100 meters. And let's say the total time, someone's going to start here. And they're going to go around the racetrack, one complete loop, and they're going to end here. And I'm asking you, and they do this in a time of 10 seconds, which is a very, very good time. So this person just ran a very good race. And if I ask you what is their average velocity, you would try to have to calculate what the average velocity is. And that's a trick question. So if I said find the average, it's defined as delta x over delta t. And in this case, their delta x is 0 meters. And one might say, why? Why 0 meters? Didn't they just run 100 meters? Yes, their distance was 100 meters. Their displacement was 0 meters. Displacement is the distance from the starting point to the ending point. And in this case, the starting point overlaps the ending point. So there's no displacement. And if you divide this by 10 seconds, you'll end up with 0 meters per second. So that would be the average velocity is 0 meters per second. If you were thinking the answer was going to be 10, what you were doing is you were finding the average speed. So you were finding average speed, which is just equal to the distance over the total time, which equals 100 meters divided by 10 seconds. So that would be 10 meters per second. So sometimes your average speed could be the same as your average velocity, but not all the time. So your average velocity in this case would be 0. So here's an example of something called an average velocity. So if we had a car that was going to travel just in one direction, let's say there's a car in Boston and they're traveling out west. So the whole time they'll be traveling out west. I'm not even going to write in any vector at all here. Let's back that up. Let's say I have a car in California and they're driving towards Boston. Okay, so in the first part of their journey, let's say they're going to travel for 2 hours at 100 kilometers per hour. Okay. And then for the second part of their journey, they're going to travel for 5 hours at 60 kilometers per hour. And then for the third part of their journey, they're going to travel for 80 kilometers They're going to travel for 1 hour at 80 kilometers an hour. And every single one of these, they're traveling to the east. So they're constantly going to the east. The question would be, what's their average velocity for the entire time of the trip? Well, I just gave you an idea of what average velocity is. Average velocity equals delta x over delta t. And if I rearrange that, then what would happen is it would be average velocity. Sorry, if I rearrange it, it would be this. Delta x equals v average times t. Okay. So, for the first part of my trip, my average velocity was 100 kilometers an hour. So delta x for the first part is going to be 100 kilometers an hour times 2 hours. Okay, so the first part of the trip, it said 2 hours, I was traveling at 100 kilometers an hour. If I multiply these two numbers together, the unit of h cancels out, and I'm left with 200 kilometers. And it's plus 200 because it's going to the east. If I do the same thing for the second part of the trip, delta x for part 2 would be 60 kilometers per hour times 5 hours. And that comes out to be 300. And if I did the exact same thing a third time, I would say the third piece, delta x equals 80 kilometers per hour times 1 hour, and that's going to be 80 kilometers. Okay. So what I've just done is they gave me the total time I was driving from the first segment of my journey on an average speed of 100 kilometers an hour, so I was able to figure out how many kilometers I drove to the east. And I did that for each segment of my trip. So how would I find the average velocity for the whole thing? Let me erase a little here. So the average velocity is defined this way. Okay, and it's going to be the total displacement. In this case, the total displacement, I've been displaced 200 kilometers to the east, and then an additional 300 kilometers to the east, and then an additional 80 kilometers to the east. So my total displacement is going to be 200 kilometers plus 300 kilometers plus 80 kilometers. I'm going to divide that by how much time it took. And the total time, it was 2 hours involved here, and 5 hours, and 1 hour. So that comes out to be a total of 8 hours. So the V average would come out to be 580 kilometers divided by 8 hours. And if I take out my calculator and do that math, it comes out to be a number of 72.5 kilometers per hour. If somebody else did that with standard units, it would work, but the standard units would be just humongous numbers if you're doing that. So with the standard units, it would come out to be 20.1 meters per second. So right here, what I'm saying is the answer would be 72.5 kilometers per hour, which is the exact same as saying 20.1 meters per second. Section 4, Chapter 2, Section 4 talks about something called acceleration. Well, acceleration gets a symbol, small letter a. It's a vector. It has a direction. You can accelerate forward. That's when we say our car is accelerating. You can accelerate backwards. When you slam on the brakes, you would say your car is decelerating. You can accelerate towards the center of a circle as you're going around a rotary or an amusement park ride. There's acceleration towards the center. It's called centripetal acceleration. So acceleration has a particular direction associated with it. And with acceleration, we would basically use words and we would say it's the change in velocity with respect to a change in time. In fact, I put it into a formula. So I put it into a mathematical formula already. So acceleration means the change in velocity over the change in time. So if I gave it a formula here, I would say it's going to be delta V over delta T. Okay. And if I expanded that a little bit, I would say the acceleration is going to be equal to v final minus v initial over. Now, instead of continuously saying delta t is t final minus t initial, I don't want to keep on doing this. So delta t is t final minus t initial. Most of the time, when we're going to record some time for an experiment, we would use a stopwatch or some digital device, and we would zero it out before we use it. So if we're always going to let this thing here be 0, always start with t initial being 0, then there's no reason to talk about the t initial and the t final. I could just talk about the t involved in the experiment. So at this point forward, I would like to say that t by itself is the time involved for the experiment. That's how much total time the experiment has happened. So here we have a formula that says a, and that's the acceleration, it equals v final, the final velocity, minus v initial, the initial velocity, over time. In life, if somebody is really good working with cars, they might say something like, my car can go from 0 to 60 in 4 seconds. They didn't use units altogether there. What they were talking about, kind of just for a moment, if I may use incorrect units, they might say my car can go from 0 to 60. They mean miles per hour. So if I use those type of units, it's going from 0 to 60, 60 miles per hour, minus 0 miles per hour. And then they're saying, let's divide it by the time. And in the case I just gave you, the person said, my car can go from 0 to 60 in 4 seconds. So we'd have 4 seconds here. That's what acceleration means. It's talking about how your velocity can change with respect to time. In this particular case, for physics, we're not in the standard units here, and we should be in the standard units in such a way that the units of time will all be the same. So I would rather use units of meters per second up here instead of this. So a better way may be something like this. So we'll keep that in mind. But 60 miles per hour, it's approximately 30 meters per second. Approximately. So I could say this. My car goes from 0 to 30. This is 30 meters per second minus 0 meters per second. And what I would do is, 30 minus 0 is 30. So this would equal 30 meters per second divided by 4 seconds. This would come out to be 7.5 meters per second. So that's what the acceleration would equal. Remember, acceleration is a vector. It has a direction. That's what that arrowhead over there means. Nobody talks about acceleration with these units, meters per second. It's too complicated to write it that way. So the way they would do that is on the side over here. If you were to take the number 7.5, if you were to take meters over seconds and divide it by seconds over 1, well, what I was taught was to multiply by the reciprocal. So what happens is I could get rid of these units right here, and I could multiply them by 1 over seconds. And if you see what will happen is meters times 1, that's going to be the unit of meters, and seconds times seconds is the unit of seconds squared. And the number would stay the same, so you'd still have the number 7.5. So down here, instead of writing it this way, I would write the unit as meters over second squared. So when they say acceleration, we're going to use the symbol in the formulas of a letter A, a small letter A. It's the first letter in the word acceleration. Just the same way as when we see the letter V, we're going to be talking about the word velocity. It's the first letter in the word velocity. When we talk about time involved with an experiment, we're going to use the letter T for the symbol in the formulas. It's the first letter in the word time. Okay. And we should be using standard units. So the units that we need to use would be meters over seconds. So I will say we need to use units of meters over seconds squared, I mean. So, meters over seconds squared. Now that squared doesn't mean anything other than the unit is squared. It doesn't mean square the number associated with it. Okay, so when you see down here how it says 7.5, the number for the acceleration is just the value 7.5. And then we have meters over seconds squared as far as units go.